Namaskar from Vijnana Bharati. Welcome everyone for Sunday Live Talk series. This is Talk 6. We are very fortunate to have Professor B.N. Jagtap with us today. Professor Jagtap is a faculty at Department of Physics, IIT Mumbai. His research interests are laser physics, quantum photonics, and the future is in even negative refraction. Prior to joining IIT Mumbai, Professor Jagtap has been distinguished scientist and director of chemistry group of BARC. He has more than 133 publications to his credit, and he has been cited more than 500 times. So we are in very august company this evening, and now I'm going to request Professor Jagtap to speak on the theme of the day, that is Professor P.C. Ray, whom all of us know as Acharya P.C. Ray, today being his memorable day. Uh, I hand over proceedings to Professor B.N. Jagtap. Thank you, sir.
Thank you, Dr. Rajwade. It's very nice that I'm speaking on this particular subject. I used to speak on this subject a few years ago, and then I graduated to talking on his book, The History of Hindu Chemistry, and later on expanded my scope of lectures. So I'm back to the square one now, talking about Acharya Prafulla Chandra, very inspiring personality. And uh, fortunately, yesterday I was connected with 100 years of uh, Anna Bahu Sate and Lokmanya Bal Gangadhar Tilak functions, both organized by University of Pune and University of Mumbai. And today I'm here for the birthday celebration of Acharya Prafulla Chandra. Friends, Acharya Prafulla Chandra Ray is a very renowned chemist that India ever produced. And this we can, as we go along, we'll see what are his contributions. In brief, we know that he is is called as the father of modern Indian chemistry. Much of his education was in Kolkata, and that too in the college established by Pandit Ishwar Chandra Vidyasagar. And his English teacher for the English literature was none other than Surendranath Banerjee. So a great influence. Uh, in that college, there was no physics or chemistry. So he used to go to the Presidency College for learning physics and chemistry. He also acquired two more languages. He was proficient in English and Sanskrit, and later he studied Latin and French while he was in the college. And then he got this Gilchrist Scholarship for Higher Studies in the University of Edinburgh. One of the criteria for the Gilchrist Scholarship was that the one who competes should know four languages. And that's why he knew Latin, French, English, and Sanskrit. There used to be only two scholarships, and one of that scholarship he obtained. And he joined University of Edinburgh in 1882. He had his BSc in chemistry in 1885, got his doctorate in 1887, and the PhD topic of his doctoral thesis was conjugated sulfides of the copper and magnesium group. And then he returned to India and became a faculty in Presidency College. Then later on, he shifted to Calcutta University. There he spent from 1916 to 1937. And after 1937, he served as emeritus professor at Calcutta University, more than 158 research papers. And the most important thing that is that one must mention here, that he was not a test tube chemist. He went much beyond that. He was an academic entrepreneur, and that's the terminology which has got currency in last few years in this country. He was the founder of Bengal Chemicals and Pharmaceutical Works, which he did in 1903. Uh, Professor Ray was a scientist, he was an educationist, he was humanist, he was a philanthropist, he was a rationalist, and patriot all par excellence. I'll bring to you some of the quotations by very, very great people and how they describe P.C. Ray. Sir Jagdish Chandra Bose said, the combination of such qualities in a single individual is indeed rare. There can be no higher example for the young generation to emulate. Uh, since last week, we have been talking about the national education policy. And there is one of the important theme there is training the teachers. And that is where we need to now understand what Acharya Prafulla Chandra Ray talked about the teaching. To be a successful teacher, especially to junior students who are just commencing a course in elementary chemistry, it is essential that he should have a neat hand in conducting experiments and that this should be so arranged as to make the lectures not only interesting but also easily intelligible. This is the passion for teaching, and this is what our present day teachers need to take example from. Apart in the teaching, he introduced also while teaching, he introduced also the social consciousness among the students. And this is his famous statement when he entered the classroom, and that was just after there is a news what he read about the suicide of a girl due to dowry. He started his lecture by saying, each one of you is a potential murderer. So the social sense that he brought into his students. And there is a very interesting statement which was made by Mahatma Gandhi way back in 1931. He writes, I had the privilege of knowing Sir P.C. Ray for the first time when Gokhale was his next door neighbor in 1901. This is one of the Congress adhivations. And I was undergoing tutelage under the latter. You know the Guru Shishya relationship between Gokhale and Mahatma Gandhi. It was difficult to believe that the man in simple Indian dress and wearing simple manners could possibly be the great scientist and professor he even then was. And it took my breath away when I heard that out of his princely salary, he kept only a few rupees for himself, and the rest he devoted to public uses and particularly for helping poor students. Uh, Professor Ray did extremely good work during the 1923 Calcutta floods, when much before the government machinery came onto the road. Professor Ray, with his volunteers, were working for the people. And on that episode, there is a writing in the Manchester Guardian. He's a very strong nationalist. He's also a real organizer and a real teacher. I heard a European saying, if Mr. Gandhi had only been able to create two more Sir P.C. Rays, he would have succeeded in getting Swaraj within a year. What a great commentary on a person. And this particular saying, what he writes to the freedom fighter Chittaranjan Das, his wife, when Chittaranjan Das was imprisoned, P.C. Ray writes, I can assure you, however, dear sister, that in serving my favorite science, I have only one idea in mind, namely that through her, I should serve my country. Our aspirations are same. God knows I have no other objective in my life. So it was the science, doing science was not only for the sake of getting name or fame, but it was for the service of the country. And that's a great feeling that the youngsters must emulate. He had a vision for India, and this is certainly a distinguishing vision. We usually talk about education as to bring in the civilized qualities in the students and so on and so forth. However, his idea was something beyond that. And this idea matches with what we think about education today. And what he said was The progress of India and Indians can only be possible through education and economic prosperity of the masses, and for later, commerce and industry are essential, and that chemistry can play a major role for the country's industrial and economic progress. And with this, he founded the Bengal Chemicals and Pharmaceutical Works in 1892. Uh, he was also associated with several other commercial ventures: the Bengal Potteries, Bengal Enamel, National Tanneries, Weighing Machine Manufacturing Company, Indian Shipping Company, publishing houses. It's an amazing personality. That's what he did not stay within the laboratory, but whatever science that he did and science he knew, he wanted to promote as a part of the growth of industries in India. And there is another facet of his personality that is here. He remained associated with the Bengal Chemicals and Pharmaceutical Works until 1939, and then he resigned. He was requested to take back his resignation. So he writes, "My joining the board is out of question, especially in view of their attitude towards the research work." Look, this is a man who's talking about it in 1939, and the aspects which we now honor today, that if you want to have a good industry and it should progress, the research has a definite role in it. You just cannot be manufacturing and selling and making profit. So my joining the board is out of question, especially in view of their attitude towards the research work. I am glad I can wash my hands clean of all responsibility in the matter of the future of Bengal Chemicals. The fixed running idea of yours and the directors had always been to squeeze out everything as long as they could offer large dividends. So the role of research in the industry is highlighted here. Uh, there are large number of research contributions of Professor Ray. As I have divided them into four categories: the metal nitrites, especially mercurous nitrite, ammonium nitrite and related compounds, chemistry of sulfur compounds, and coordination compounds. Let's look at some of these contribution. The first one is mercurous nitrite and related compound. We know that mercurous is unstable species. In a solution, it will disproportionate to give mercury plus 2 and mercury metal. In the same manner, nitrite is also an unstable species. And therefore, what he does here is take two unstable species, one cation and one anion, and creates a stable species. This is a mercurous nitrite. And this is, you take mercury in excess and add nitric acid, and you get the yellow crystals of mercurous nitrite. And then he plays around with the different mercury alkyl or mercury alkyl ammonium nitrite, so on and so forth. He was specifically interested in chemistry of mercury, and some part of that we will see when we talk about his work on the Hindu chemistry. He was interested in the synthesizing the calomel, and that's how his interest in the mercury started. He produced another compound, which is a hyponitrite. With again the same thing, you get the mercurous nitrite, and from there you generate this mercurous hyponitrite. So these are the two monumental contributions in the chemistry of mercury. He was the first scientist to synthesize crystalline organic sulfur compounds with the high molecular weight. So you have this ethylene dibromide, and then you have this disulfide, and then they condense together and you form a very large polymeric compound. And this first time it was formed. And also the condensed heterocyclic compounds, which are here, triethylene trisulfide, triethylene tetrasulfide, and sulfone compounds. He also had contributions in the coordination compounds, particularly the coordination chemistry of platinum, iridium, gold with the organic sulfides at ligands. And here are some examples here. This is the with the iridium. You have He found that there are two isomers. One is the red and orange. The orange isomer is of the type MX3R2S3, and that is the first time such a compound was reported. And he also investigated the rich chemistry of this M there, with the M as iridium, rhodium, osmium, and ruthenium. And the red isomer is little complicated, and that the structure of this is shown here. Uh, the writings of Professor Ray include India Before and After Mutiny, the Essays on India, A History of Hindu Chemistry, Volume 1 and Volume 2, and Life and Experiences of a Bengali Chemist. Uh, the famous book is The History of Hindu Chemistry. This is, I have brought to you the cover page of Volume 1, but there is also there's Volume 2. And you can read here the title here, History of Hindu Chemistry, the earliest times to the middle of the 16th century. So that's the time frame that he considers for the Hindu chemistry. Mind you that this word Hindu should not be taken in the communal sense. Uh, there are different kinds of ancient chemistry. There's an Egyptian chemistry, there's a Chinese chemistry, there's a European chemistry, and therefore the geological indicator for the chemistry which was developed in this part of the world is called the Hindu chemistry. So it should be taken in that spirit. It's a monumental work on the glorious achievement of ancient Indians in the field of chemical and medical sciences. Uh, it was Marcellin Berthelot who influenced him a lot. The Berthelot had written a book on chemistry in Europe, that is the ancient chemistry, and he took inspiration from that and wrote this history of Hindu chemistry. And Berthelot, in turn, wrote a long review article in this particular journal, Journal des Savants. The Swedish chemist Arrhenius, we know the Arrhenius equation in his book Chemistry in Modern Science, quotes from this work. And the German chemist Lippmann also has summarized his work on Hindu chemistry. The first volume came out in 1902, the second volume in 1909. The nationalist in Professor Ray, you can see from this particular episode. He was delivering a lecture at Lahore University, and he was talking about the contribution of Indians in the field of chemistry, and he was annoyed by some expressions of sneer in a young Englishman present in the audience. But he did not display his anger. At the end of his lecture, he took a sample of Makaradvaja, that is mercuric sulfide, in his palm and said, "My ancestors made this remarkable chemical when the ancestor of the young Englishman were roaming in jungles wearing raw hides." So he was there to talk about the priority of Indians in establishing chemical processes and also the metallurgy and so on and so forth. Uh, if you read his book, The History of Hindu Chemistry, the first thing that strikes you is what is his idea? Why does he write this book, History of Hindu Chemistry? And read this. He says, the capacity of a nation must be judged by what is independently achieved in several fields of knowledge and branches of literature. Mathematics, including arithmetic, algebra, geometry, astronomy, phonetics, philosophy, grammar, law, philosophy, and theology. Attempts are made by certain schools of European scholars to prove that the Greeks were the pioneers and the first teachers of the world in the field of medicine, as in several others. It is curious to reflect that the upholders of Greek culture are often ready to twist and torture facts and conclusions to serve their own purpose and reserve to themselves the benefit of doubts as regards the dates. But whenever the priority of Hindus is unquestionable, an appeal is made to the theory of common origin and independent parallelism in growth. These scholars seem to smart under a sense of injury if they have to confess that the Europe owes an intellectual debt to India, hence many a futile attempts to explain away any positive historical facts. And in this book, he brings up everything that the priority of Indians in establishing chemical sciences and metallurgy. Now, I have a few slides here, which have just to give you an introduction that these monuments have been there for hundreds and thousand years in the country. The Iron Pillar of New Delhi, this is 375 to 414 AD. The description is given here, it's a 6 tons and so on and so forth. It's a pure wrought iron, 99.72%, and its chemical composition that we know now is given there, and some of those numbers which are there in color font, that is phosphorus and sulfur and manganese, these compositions make this pillar rustless. That's very important to note. We also know that that iron pillar is not the only iron pillar. There is another iron pillar at Mukambika temple near Mangalore. It's a smaller one, 8.7 meter height and weight of 500 kg. It also does not rust. The same iron, non-corrosive wrought iron beams you find in the Sun Temple, Konark, in the 9th century. And we also know about the iron pillars, Dhar, the 10th century. These are the tallest non-corrosive iron pillars in the world. And on this, the James Ferguson had written something wonderful. The Hindus at that age, 400 AD, were capable of forging a bar of iron longer than any that have been forged even in Europe up to a very late date, and not frequently even now. So this was the progress that the Indians had done in the metallurgical processes, the iron metallurgy, way back in 400 AD. And also we also know the contribution of Indians in the copper metallurgy. This is the copper statue of Gautam Buddha. And also we know the alloys which were made in those earlier days, the coin of Samudragupta or the bronze Jela statue of Nataraja, so and so forth. What essentially Professor Ray does in his 2 volumes is, from the Vedic period until the middle of 16th century, he demonstrates that the Indians had made remarkable progress in material science and metallurgy, including atomistic basis of chemistry, extraction, preparation, purification, characterization and application of metals, alloys and chemical compounds, and chemical processes such as calcination, sublimation, distillation, steaming, fixation, casting, etc. for large scale production. This is extremely important. The kind of pictures that we have seen can show that really they were working at the industrial scale operation. And in several of these endeavors, the Indian chemists were far ahead of their counterparts elsewhere in the world. And that is why these 2 books are extremely important to see what was the progress in chemistry and metallurgy the Indians had. And we must thank Acharya Prafulla Chandra Ray, the father of modern Indian chemistry, to provide this great idea to the next generation. I'll just briefly go. This is not a talk on the Hindu chemistry, but it would be very interesting what a painstaking work Professor Ray has done. He brought in the timeline and also who were the Indian chemists and their works. I have just compiled in a few slides. The chemical sciences, Professor Ray divides into 5 periods: the Vedic period, that's up to 600 BC, the Ayurvedic period, 600 BC to 800 AD. There's a transitional period, 800 AD to 1100 AD. Transitional period, you find that there is a lot of inorganic chemistry and inorganic compounds come in as medicines. And then there is a tantric period. There is a Hindu tantrics as well as Buddhist tantrics. That period, 1100 to 1300 AD, a lot of work was done in the chemical sciences and setting up the processes. And then you have the iatrochemical period, 1380 to 1550, and that's where he stops. After 1550, you can see this is where the Europeans had started entering in India and all that thing. So he stops at 1550. The Indian chemists that he mentions in the Vedic period are from Agnivesha to Kapila. In the Ayurvedic period, the Charaka, Shushruta, Vagpata, Varaha Mihira, Patanjali, Kautilya. Of course, Patanjali and Kautilya have some writings on chemical processes. The transitional period, of course, this is the golden period of chemistry where Nagarjuna with his work Rasaratnakara, Kakashaput Yantra, Arogya Manjari, Yogasara, Vrunda with his work which is written in the bracket Chakrapani, Vagbhata, Gangadhara. These are the people in the Tantric period, Govindacharya, Bhikshu Govinda, Somaveda, and everybody has contributed several books. And you can see here Sarveshwara Rasayana, Dhatuvad, Rasahridaya, and so on and so forth. And in the iatrochemical period, we have large number of chemists, Nityananda, Vishnudeva, Govinda Dasa, so on and so forth. Also, there are several other works by other chemists which are not listed here. Like the problem in the history is that there are some people who take nicknames and write in a different ways. So these are other writings in chemistry and metallurgy. This is something which I would like to bring it directly from Acharya Prafulla Chandra's book, History of Hindu Chemistry. And this is where he also provides a translation. This is Rasaratna Samuchaya. Now, these are the beginning portions of this. Rasotpati Naam Prathamodhyaya. Now, there is a Sanskrit writing there. And very important, and this is the way the historian would start looking at the development of chemistry. And this says, Adima, Chandrasena, Lankesa, Visarada, Kapali, Matta, Mandavya, so on and so forth, up to Hari. These are the 27 experts of Rasa Shastra. So this is Saptavisham Shatni Sankyakas Rasam. This. Then he adds the Bhairava Nandi and Swachanda Bhairava, Manthana Bhairava, so on and so forth. They are the people who got the application of Maithi, Mahadeva, Narendra. So it's a big tradition of chemists that existed in India. And next stanzas read like this: the treatise on well-tried mercurial and minerals named Rasaratna Samuchaya, adapted to the treatment of diseases, is being compiled by the son of Simhagupta after having consulted the works of the aforesaid adepts and others. So this is Rasaratna Samuchaya. It refers to all those books, the kritis of all the earlier chemists, and he writes this. And this is one taken as a materia indica in a true sense. It will treat mercury, minerals, metals, construction of apparatus, and mythical formulae for purification of metals, extraction of essences, liquefaction, and incineration. So Professor Ray provides this translation wherever it is required. And timeline, if you read through this book, then you can understand how the chemistry and metallurgy evolved in India in the different periods. The Vedic period, it was primarily medicinal and metallurgical chemistry. Then the Ayurvedic period, the constitution and properties of matter, the concept of Anu, and so on and so forth, preparation of gold, silver, copper, iron, lead, alkalis. In the transition period, identification of minerals, copper compounds, use of mercury and lead, caustic alkali, soap, formula for eye ointment, hair dye. In the Tantric period, the details of experimental chemistry, chemical apparatus, crucibles, colors of flames, copper from pyrite, brass from calamine, zinc from calamine, purification of mercury, coloring of metals. And finally, in the iatrochemical, you have now a systematic chemical classification. And this is different from what we learned today, but nevertheless, it's very interesting. It's a complete laboratory practices, initiation into disciplines, and extraction of gold, silver, copper, zinc, iron, tin, lead, antimony, uh, bell metal, and so on and so forth. There's pretty good progress by 1550. The important milestones is also you can see from Professor Ray's book. 2500 to 2000 BC is the gold, silver, copper, lead, gold, silver alloy, some minerals. 1500 to 800 BC, tin, iron, glass, fermentation, canning, medicinal chemistry. 600 to 400 BC, the brass, steel, colored glasses, ink, amalgams, vegetable dyes, some part of the atomic theory, concepts of compound formation. 10 to 400 AD, chemical combinations, preparation of alkalis, use of minerals in medicines. 400 to 600 AD is the iron pillar, pure wrought iron. The statue of Gautam Buddha, which is pure copper, 99.7%. And then the processes for hardening of steel, arsenic, cosmetics. 800 to 900 extraction of zinc, very important development. And uh, I'll not be talking about it, but this is something where the industrial level production of zinc was going on in the country. And that continued until the period of the Mughal, the Akbar, because there is a statement somewhere that the Badshah asked his minister, which are the top five export-oriented materials that we produce in India, and that zinc was one of those five. Uh, and also then you have the medical uses of calomel, perfume, so on and so forth. The important milestones in the Indian metallurgy were the copper mines way back 2500 to 1800 BC, use of copper tools throughout India. Iron technology was developed around 1400 BC. Copper smelting, this was 1200 to 1100 BC. Again, 400 BC, King Puru presents steel to Alexander. This is normally a king would give gold to another king, but Alexander said that he wants the Indian steel, and that is what was presented. The iron pillar was fabricated and it was shifted to Delhi in 1050 AD. The copper statue we already talked about. The wood steel for making high quality swords. This was developed in the 6th century. And then it used to be a regular material exported to Damascus and Syria. And today we know that this is the microcarbide within tempered martensite. This was done throughout South India. In comparison, if you look at the progress of chemistry in Europe, well, you have the atomic theory by Democritus, 460 to 370 BC. Then much of the period was alchemistry, and then in 1214 to 1294, Roger Bacon, he begins the experimental chemistry. 13th century was arsenic, and 1492 was antimony. The medicinal chemistry started essentially with Paracelsus. That was in the 1493 to 1541. The sulfuric acid was done in the 15th century. We have references which Professor Ray points out that in Indian chemistry metallurgy it was much earlier. The beginning of modern sciences started with the Francis Bacon, 1561 to 1636, and that is where essentially the developments in India had stopped. They got frozen, and this is where the euro started. This was the Renaissance period, and then the Robert Boyle's gas laws came in 1620s and this. Then the zinc came in 1695, which was at least 800 years before that happened in India. The oxygen, the laws of definite and multiple proportions, these were developed in the 18th century, and dyeing came in the 18th century. So this is what is the major period that the Western chemistry took a fillip, and by that time we were all frozen. Now I'll bring to you a few representative examples. This is all the stories which these are the facts and figures collected from Professor Ray's book. However, to some it may appear as stories, so there are definitive examples which I'm going to bring them here. This is the Chandogya Upanishad, and look, this shloka is in a slightly different context. It says that if you are doing a yajna and that yajna gets broken, then there is a way to join this. And the simile what is given is just as one would join gold by salt, silver by gold, tin by silver, lead by tin, iron by lead, wood by iron, and wood by leather. That's the way we must join this. Sorry. Brahasahita also talks about a very special alloy, a mixture consisting of 8 parts of lead, 2 parts of bell metal, and 1 of iron. Iron has been mentioned as mentioned by Maya and is to be known as Vajra Sangataka. Vajra Sangataka. Then Rasarnava is another treatise, interesting one, and the way it is written is so interesting. It talks about the reactivity of various metals, and how does he write it? O goddess, Shrunu Lohanyataha Param. O goddess, listen now to what I say about metals. Loha also is used for metals. Gold, silver, copper, iron, tin, and lead. Swarnam, rajatam, tamram, tikshnam, vangam, bhujangamam. Lohantu shadivadam tacha yathapurvam tadakshayam. These are 6 metals, and their resistance to rusting is in the order in which they have been mentioned. That is, the corrosion resistance of 6 metals is as follows: gold greater than silver, greater than copper, greater than iron, greater than tin, and greater than lead. This is what today we know as the electrochemical series. The Rasaratna Samuchaya talks about large number of ions, and this is Mundaloha, Mundam Tikshnam Chakantam Cha Triprakara Maya Smritam. There are 3 kinds of iron, that is Mundaloha, Tikshnaloha, Kantaloha. In today's language, this is a cast iron, wrought iron, and carbon steel. And each one of them, Mundaloha has 3 types, Tikshnaloha has 6 types, and Kantaloha has 5 types. Then there are ways to prepare various alloys. Ashtabhagena tamrena dvibhaga kutilena cha. Bronze is obtained by melting 8 parts of copper and 2 parts of tin together. This is a test. This is Rasaranama provides a test for pure metal. Now read it in English. A pure metal is that which when melted in a crucible does not give off sparks, nor bubbles, nor spurts, nor emits any sound, nor shows any lines on the surface, but is tranquil like a gem. And then the reactions of sulfur with metals was well known with the different metals. And this is a very interesting way of putting those reactions of sulfur. And what it says is there is no metal that cannot be killed by a lion called sulfur. So this is the Gandhaka is Gandhaka Keshari. So this is there is no metal that cannot be killed. So this is the reactivity of sulfur with the. It also during all these chemical practices, the flame tests were also developed, and these are very interesting things to look at because today we start the chemistry practicals with the flame test. This flame tests were known those earlier days, and what this shloka says is colors of the flame of metals are: gold gives yellow flame, silver gives white, copper gives blue, wrought iron gives black, tin gives ash color, lead gives dirty fire color. The important thing is the diamond. Diamond gives many colors. This is the thermoluminescence of diamond. It will give large number of colors. Now, the names of the chemicals. This is where painstakingly Professor Ray really explains what are these. The copper sulfate was known as, the name in Sanskrit is Sasyaka. Kasika is iron sulfate. Saurashtri is alum. Gairika is ferric oxide. Manasilla is arsenic sulfide. Phenasma Bhasma is arsenic. Haritala is arsenic sulfide. Makshika is copper sulfide, and so on. Vimala is a rust of iron. Neela is indigo. And then several other chemicals have been described. And Professor Ray points out Hingula is a mercuric sulfide. Silajatu, Yavakshara is a potash, and so on and so forth. You can see that metals as well as the salts have been described there. And how do we know that Makshikam means certain chemical today? Well, these are Rasaratna Samuchaya provides those. Atha Makshikam, Atha Vimala, the characteristics and the usages. Atha Chapala, Atha Gairikam, Atha Navasara, and so on and so forth. This is another important aspect which Professor Ray brought in from the Hindu chemistry. That is, there was a definite classification of chemicals, and they were classified in 10 different categories. The Maharasas, these are main chemicals. Uparasas are subsidiary chemicals. Samanya rasas, these are the common chemicals. And then Ratna, Dhatu, Visha, Kshara, Amla, Lavana, and Lohavasma. So these are the metallic powders, that is Lohavasma. So these were the 10 classifications of the chemicals. They are different from the way we classify chemicals. Today, the Maharasa, these are the main chemicals. Which were the main chemicals there? There are 8 main chemicals, which are iron pyrides, asal, then copper sulfate, sulfides, calamine, which is the zinc mineral, cinnabar, and so on and so forth. Makshikam, Vimalam, Shailam, Chapalam, Rasakastata. So that these are the Maharasas which are expressed there. Then there are Uparasas, subsidiary chemicals, Gandak, Gairik, Kashis, Tuvari, Talak, Manasila, Anjana, and Kankushta. That is the excreta of baby elephant is also a chemical, subsidiary chemical which is to be used. Basically, it is as a source of carbon. The Samanya rasas, the common chemicals, were Kampilya, Gauri Pashan, that's arsenic oxide, Navasara, Varataka, Agnijara, Girisindura, Hingula, and so on and so forth. And you have this definition, the Amla, both organic acids and inorganic acids were known. Mahadravas Dravakas Rasa, this is something like a sulfuric acid, or there is also a mention of Dahajala, that is burning sulfur with a small piece of borax, or take alum, that is because you have the sulfate, then green vitriol, saltpeter, borax, mix them and distill, then you get that acid, which is most likely is the sulfuric acid. The ksharas, there were Trikshara, Tankana Ksharo, Yavaksharo, and so that is borax, potassium carbonate, and soda. And also they were derived from the ashes of certain plants, Apamarga, and so on and so forth. We'll refer to one example a little later. There were 6 types of salts. Samudra is sea salt, Saindava, rock salt, Bida, Saurvachala, that is potassium nitrate, Romaka Lavana, which is a mixture of sodium carbonate, sulfate, and chloride, and Chullika Lavana. This is the chemical apparatus. Now, this is where a very important contribution of Professor Ray. In the chemical literature, there are so many chemical apparatuses are mentioned. Shila Yantra, Pashana Yantra, and so on and so forth. Now, what Professor Ray does is, based on the description, he makes picture out of them. But I'll show you those pictures a little later. And for example, there are definitions of crucible. Mushnati doshan mushaya sa musheti nigatyate. The crucible is an instrument used for purifying metals, and the materials used for crucible are clay and iron. And these are the pictures. the Dheki Yantram. These are the pictures which are provided in History of Hindu Chemistry by Professor Ray. Valuka Yantram, Dola Yantram, Svedani Yantram. You can see there is a air provided from here, the Svedani, the Dhupa Yantram, Koshti Yantram, Patana Yantram, Adhaspatana Yantram, Tiryakapatana Yantram. Now, this is a very important one, the Tiryakapatana. Tiryakapatana Yantram means it's a downward distillation, which the Indians discovered pretty early, Tiryakapatra Yantram. And the very reason for this was, you can see here that this shloka, which says, the tradespeople fraudulently adulterate mercury with lead and tin. Hence, it is to be freed from these impurities by means of three distillations as given in Tiryakapatana Yantra. So, this was specially made for purification of mercury. And I will not be covering this, but this downward distillation process played a pivotal role in the zinc extraction. And that is where the industrial scale zinc was produced. Uh, how to establish a chemical laboratory? Well, that description is also given, which Professor A helps you to understand. The chemical laboratory must be established at a place where there exists plenty of medicinal plants and water. And at the end, this is something interesting. Who can be employed on these chemical laboratories? Those who are truthful. See, this is an important one. One should not concoct results. One should be truthful. If they observe something, then that is the observation. Faithfully, they must record. No plagiarisms. Free from temptations. And are well versed in knowledge of drugs, plants. And look at the next word. Languages of many countries should be employed. And that languages of many countries is because there was a trade which was going on all across Asia, and all these chemical processes, the metallurgies, and so on and so forth. There's a huge export which used to take place from India. Uh, Now, this is something which I'll spend few minutes. Professor Ray, in particular, tested this ancient Indian chemical practices. That's a scientist in him. That suppose, for example, in Shushruta Samhita, there is a process given for preparation of alkali. So this is the shloka which I have brought to you. Its English translation is like this. Some well-grown trees in the forest are cut into logs and piled in a place free from strong wind. Limestone seashells should be placed on the piles and then set on fire by stalks of dry plant. When all the wood is burnt out, the fire extinguished, the ashes of the logs and the burnt lime are collected and kept separate and dissolved in water. The extract of the ashes is then mixed with the lime water to get the lye, which is separated from the precipitate by filtration. The solution is concentrated to different extent by boiling, and it is possible to get dilute, mild, and caustic alkali. Now, what Professor Ray does, he takes that plant. One of the plant he takes is apamarga. Okay, and now he takes the leaves, a stem, and the roots. And being a chemist, he takes the ashes and gives it for elementary analysis. And what he finds is the leaves contain 17.84% potassium oxide, the stem contains 32% of potassium oxide, and root contains 28.58% potassium oxide. So this potassium oxide, when it comes in contact with water, will give you potassium hydroxide, that's an alkali. But the process is very interesting, as described there. You also have the seashells, and then you heat. What happens here is calcium carbonate decomposes to give you calcium oxide and carbon dioxide. Then this potassium oxide from these ashes combines with the carbon dioxide, give you potassium carbonate. This calcium oxide in contact with water gives you calcium hydroxide, and this calcium hydroxide in reaction with potassium carbonate gives potassium hydroxide and calcium carbonate. That is where you filter it. The calcium carbonate will be filtered out, and the solution will be potassium hydroxide, and that's an alkali. If you want a concentrated alkali, you heat it and get it concentrated. Another interesting thing which Professor Ray studies is the preparation of calomel, is Hg2Cl2, and this is a very important chemical which is used in the Buddhist as well as the Hindu religion. Uh, I'm told that this is a one which is taken for long life. Now the recommended procedure is purified mercury, gairica, that is ferric oxide, alum, rock salt, khari lavana, that is potassium sulfate, and red earth. And then there is a procedure given: place on fire a pot containing this mixture and heat for 4 days. The pot is covered with the lid. The white camphor-like solid deposited on upper part is the desired product. And then there is a chemical reactions which go on and which will tell you that this gairica, which is used in this, acts more like a catalyst. And that is what finally your product is, Hg2Cl2. Uh, Once you read that book, you'll find that many of these developments in chemistry were used to man and which influenced progress of human civilization. They originated in India much before the corresponding developments in Europe. And this is an extremely important thing. There is one more aspect which I mentioned a bit earlier, that a chemist was supposed to know languages of many countries. The reason for that was the Indian craftsmen, they acquired mastery and they made innovations so that the Indian products like metals, silk, cotton, paper, cosmetics, perfumes, dye stuff, glass, porcelain goods became much valued and preferred articles in foreign countries. And this is where we forget the contributions of Indian chemists and metallurgists. When we talk about ancient India, we say that, oh, we developed great philosophies, we developed mathematics, and we also developed the Jyotisha Shastra. Uh, However, we forget many times that India was a spiritual leader, a leader in knowledge, and also it was a very prosperous country. And that prosperity came because of these Indian craftsmen. They did all this chemistry and metallurgy, and their work, their contribution, that is what you find in the history of Hindu chemistry, volume 1 and volume 2. Now, just to support this, I'll bring something which we know today, and this is the history of world GDP. This is August Madison, University of Groningen. He wrote in economics, and he provided this graph. You can see here bar charts, out of which the brown portion is the contribution to the world GDP by China, and then there is a pink portion which is the contribution of India to the world GDP. And this is the year 1 AD. You can see here at that time India was contributing more than about 50% of the world GDP was coming from India. And that stayed to a large extent up to year 1700. And all this, the trade which was done in this case was the metals and silk and cotton and all kinds of dye stuff, glasses, and all that, the iron for making swords and so on and so forth, which was going out of India. Uh, I have been reading some old references in which I was struck with a very interesting episode, incidents that Yuan Sang, he entered India to Tibet, and he left India via Sri Lanka. And then he describes that there was a regular ship service from Sri Lanka to all the way to China, and there were huge ships. We were carrying lots of materials, the iron bars, and each ship having hundreds of passengers. So this was the trade which the Indians used to do, and that made India a very prosperous country. And this is what we we need to remember, and this is what has been highlighted very nicely by Professor Ray. Finally, Professor Ray has made an interesting statement. The Indian nation, with its glorious past and vast talent potentialities, may yet look forward to a still glorious future. And if the perusal of these pages means volume 1 and volume 2 of History of Hindu Chemistry, will have the effect of stimulating my countrymen to strive to regain their old position in the intellectual hierarchy of nation. I shall not have labored in vain. So, this is what he expects from all of us. This is the book I have brought in here. He says that glorious past and the potentialities of the Indian nation, what existed. With this writing, the next generation should take some figure out of it and should work again to get back to that old position of in the intellectual hierarchy of nation. If that happens, whatever I have done, whatever I have written in this book is worth it. uh, there is very interesting. I'll end with an interesting statement, very uh, apt statement by Dr. Rajendra Prasad. Acharya Ray revived and handed on the flame the pursuit of truth, which once burned so brightly in India. And he has left behind an example of service and sacrifice for his countrymen to follow for the fulfillment and enrichment of their lives. So, this is that pursuit of truth which existed in India in the earlier period. During some dark period, we lost that, and this was again revived by Acharya Prafulla Chandra Ray. And he not only practiced his chemistry, not only uh, did the test tube chemistry, but also took it to the next level. And that next level was the industrialization, manufacturing. And that's what I have been always campaigning, that the 2nd August should be celebrated as an academic entrepreneurship day. And every school, every college, every university, we must take it and say that, look, here is a man who did best of the chemistry, best of the science, produced so many papers, and also did manufacturing, established companies. And this is what will take India to the right future. With this, I end my presentation, but there are lots of sources which from where I have taken this material. The Prafulla Chandra Ray's volume 1, volume 2. One first was published in 1902, second one is 1909. There's an interesting book by Vinay Kumar Sarkar, The Hindu Achievement in Exact Sciences. The soft copies are available on internet. D. Banerjee provides a very interesting account of uh, life of Professor Ray. And these ones, the Biswas 2 articles, the Caddock's article, particularly in the Endeavour, these are some of the articles on extraction of zinc and how fine chemistry of zinc was done in those ancient days. You can read about it. This is in the Indian Journal of History of Science. And of course, the last one, we have been also trying to work on some of these things, whether the ancient chemical knowledge can it be used in today's context. With this, I thank you and I'm open to the discussions. Yeah, that's a very interesting question. What message you would like to give to today's chemists and scientists? And this is what I have been also doing personally for last 7 8 years. Can we translate our chemical knowledge into something which is useful to this society. We have got into that race of publications and publications and publications, which is really harming the the scientific culture that we once talked about. In this context, I always give one example, and that example is, I have not brought that slide, otherwise I would have explained to you in a different way. There is a concept called Pasteur's quadrant. What you imagine is you draw the x-axis and say that x-axis is applications. So whatever science I do, it has application. Either it has application or it has no application. If it has application, you are on the positive x-axis. If it has no application, it is you are on the negative x-axis. Then you draw y-axis and draw that y-axis. If you are doing this, is y-axis is for fundamental science, fundamental knowledge. So if you are really doing for the knowledge, is taking the frontiers of knowledge ahead, then you are on the positive y-axis, and then if you are not, then you are on the negative y-axis. So now you have got a 4 quadrants. You can imagine them now. Now you can see the first quadrant there, where there is a knowledge is yes, you are contributing knowledge, and you are also contributing to the application. This is the quadrant where all the chemists, or for that matter, all the scientists should position themselves. And this is particularly called as the Pasteur's quadrant. You know, the Pasteur, he was not interested in solving some problem. He wanted to know why milk gets spoiled, why vinegar gets spoiled, why chicken get cholera. And through this research, he established the discipline of microbiology. So he did both fundamental science and its application. This is where we need to position ourselves. Now, I have been also telling our Indian scientists, now please don't mind my language now, that there is a third quadrant there where no fundamental knowledge and no application. If you look at much of the Indian science falls into that. I call it as a no-no quadrant. There is no objective for doing science. The objective of doing science is other than knowledge and other than application, all the work will end up in that quadrant, the third quadrant. And that is where, suppose if I am a faculty and if I am going to get promotion, if I write 2 papers, whole objective of doing science is to get a promotion, then all my work is going to land up in that third quadrant. Howsoever money you provide to me, this is what will happen. We start this process in the PhD. Oh, if you want to get a PhD, you need to have 2 publications. And the student works only for his publications, not for providing any fundamental knowledge or not for giving any applications. This is something, the distortion that has happened, and we need to correct it. And Acharya Prafulla Chandra gives you that idea that look, doing that test tube chemistry is no use. Can you do this? Can you do that? Can you make money out of it? Today's world is that see, we used to have in India a concept like Lakshmi and Saraswati. They do not stay together. The modern times, with Saraswati, you should bring Lakshmi. This is what should happen, and that is what we call as the academic entrepreneurship. But this is what we need to consolidate. Well, this is another interesting question that if you really need to do what is the scale of production? Well, I can give you very simple example. This is what was tried when I was in Baba Atomic Research Center. See, the water in India, in something like 200 districts, there is a fluoride content in it. And if the fluoride is about 2 ppm in water, then it causes lots of health problems. But there is no way to measure fluoride at the field. I mean, you cannot bring the water and test it in the laboratory. Such facilities you don't have. On the spot, can you do it? And one chemist, he used innovation and he said, look, I have this chemical. You take water and put these few drops of this chemical into this water, and if it gives yellow color, that means the water has fluoride more than 2 ppm. Don't drink it. This is what has been now used all over the country, and UNICEF declared that innovation as one of the best innovations in the water chemistry. uh, that kit is named as number one kit. What is the quantity that you require here? A small bottle of 50 ml will last you for 1 year. So we're not talking about huge production. And what this was done at Bhabha Atomic Research Center was that this small process, of course, this chemical is very interesting one. Uh, this process was given to the entrepreneurs. You start your entrepreneur. You start testing water, you start doing it. Some money was taken from there, which was very peanut. And with that, we could establish more than a dozen entrepreneurs all over the country who did water testing on a regular basis and helped people. So one should not say that, oh, I need a very large scale production. Small scale production is also important. Now, I will also turn back the question to the audience. You see, when the COVID-19 pandemic started in India, there was a lot of enthusiasm was shown by people that, oh, we'll do this, we'll do this. I was particularly contacting engineering colleges and saying that, hey, can you do this ventilator design and all that. Unfortunately, the way we have been teaching our engineering students have not seen a ventilator. Let me make that statement. So expecting them to now design it is a different story. Then people jumped onto this UV light based disinfection devices. I was in contact with some people, they were discussing with me. The question that happens is, well, this is an old hat that the ultraviolet rays will kill bacteria and viruses. But where is that mercury lamp produced? Are you going to buy a mercury lamp manufactured in China and make this device in India, and will it become economical? Now, this is where it fails. The ventilators did not go far because you require a gas monitoring and controlling device, which is not produced in India. So, when the country was facing such a great danger, what was our academic community doing? Was it helping the country? We did not come up even with a good epidemiological model for spread of COVID-19. This is where I say that we need to do high level work. But that high level work also must connect to some application for the nation building. If it does not happen, then I am working only for my own satisfaction. And let's not make a statement which one of my friends used to do. He said that, oh, you have seen Kumbh Mela, the 10 lakh sadhus gather together. The whole society feeds 10 lakh sadhus. So it can also support 10 lakh scientists. I said, look, this is a very wrong logic that you're giving me. Uh, so that is mean our conferences are also like Kumbh Melas. Is that the way we are going to look at it? The science has a definite role, and that definite role is the economic prosperity. If it cannot be done, then and that is what the ancient chemists showed their way. This is the way the prosperity can be brought in. Yes. Uh, Well, there are, I did not provide the details of the chemical sciences because or the ancient chemical sciences, but let me see if I got some slides which I can help you with. Uh, well, it will take me time, but I can tell you this that uh, the iron which was there is a Nobel laureate, I forget his name. He visited India and then he made a very interesting statement that the nanotechnology uh, preceded nanoscience by hundreds of years. And the example that he gives was that uh, the swords which were prepared out of that iron exported from India, that they had uh, carbon nanotubes present there. Remember one thing, nobody knew about the carbon nanotubes at that time. But there were, now you are talking about the new materials. Yes, whatever the materials you are talking about, the calomel. Today, with the knowledge of chemistry, you say Hg2Clt is such a simple compound. What is new about it? Would you talk about this chemical in the same manner 1,000 years ago? 1,000 years ago, when people did not know sulfuric acid, somebody brought in sulfuric acid. Would you say, is that new? So, new and old has to be assessed at the level of which year of development of science you are talking about. If 99.7% pure copper can be produced in the 4th century, then do you not think that it is great that people could do it at that time? And this particular copper smelting process existed until 18th century, 19th century in India. What had really happened was, this is also what was explained by some historians, science historians, that as long as the Indians were operating the mines, the copper and iron mines, they had preserved this art, they preserved this science. However, when the British government stopped this, their participation in mining, and the British East India Company took over the mining, the Indians lost that knowledge. How to produce the best quality of iron, best quality of copper, so on and so forth. So everything that was done at the time was something new. Probably I can give you another talk at a later time, fixing that, well, this is the new aspect and this is not the new aspect. At the same time, we must be little cautious in our approach. And this is where Acharya Prafulla Chandra was. There were mentions somewhere in Sanskrit that the Indians knew the gunpowder, the chemistry of gunpowder. And Acharya Prafulla Chandra goes through those shlokas, and then he says, this Sanskrit is not the Sanskrit of 10th century or 11th century. This is the new Sanskrit. And therefore, this certainly did not exist in India. And now, why I particularly brought this, you got to be very, very honest when you come to this scientific things. You know that during this COVID, there was sudden some messages which were getting the messages on the social media that this was relating to the hydroxychloroquine, which is the anti-malarial drug, and it was said that it would have efficacy for treating COVID-19. And then in social media, we had, oh, this Acharya Prafulla Chandra was the one who discovered this chemical. I don't know who started it. And I have seen best of the chemists in this country joining that and saying that, yes, 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 this is what it was. Now, remember one thing, the hydroxychloroquine was discovered in 1945. And Acharya Prafulla Chandra breathed his last in 1944. Okay. The Bengal Chemical and Pharmaceutical Company, which was founded by Acharya Prafulla Chandra, used to manufacture this compound, but they had stopped it decades ago. So they didn't come. And another important point was that there was some chemist who proposed that, Acharya Prafulla Chandra Ray, he worked on chloroquinol, not hydroxychloroquine, and which is an antifungal drug. So we should not be doing this, taking unnecessary credit for something. And if Acharya Prafulla Chandra Ray were to be alive at this time, he would have he would have fired all of us and said, "Look, I didn't do this. Why are you doing this?" So that standing, that honesty we must keep, and that is the only way we can progress in science. Well, that's an interesting question. NEP 2020. I have been talking about NEP in other fora, so I'm going to keep quiet as of now. Well, the general structure of NEP 2020 sounds to be good, uh, but of course, see, the generalities are not going to be important. What are going to be important are nitty gritties. Uh, and you can see in NEP 2020, so much of stress has gone on, is being given on teachers training. It's extremely important that we should train our teachers in a manner that they can build the younger generation with all this, the curiosity, and all that should be put in. I have been also talking, that's just to give you a little bit an example, where do we fail in the education, not relating to the education policy. You know, there is an international PISA test, PISA. You can go onto the internet and find out. This is a test which is given to the children of 14-year-old, and any country can participate. Uh, there is a science test, maths test, and some grammar test, language test. We appeared, India as a country, appeared in this test in 2009. We selected two best schools, one from Himachal Pradesh and one from Tamil Nadu. Both competed. And at that time, if I remember, 157 countries had competed. Our number was third from the bottom. And then we said, oh no, we are not going to participate. Now there is a pressure. The present government is taking a bold step that we should be competing in 2021. Now, why does it happen? I mean, they were asking very simple questions. Simple, if you have taught our students how to reason it out. Unfortunately, we have not. Uh, I still take some sessions in the schools. One example, one question I'll tell you. Helen has a bicycle, and she rides the bicycle from home to river, and she covers 6 kilometers in half an hour. On the return, she takes a shortcut, and she covers in 4 kilometers in 15 minutes. Question asked is, what is the average speed of Helen? You know how our students solve it? They find out the speed for the onward journey. They find out the speed for the return journey and take average of this. This is what they find. They have not been taught in the schools that average speed is the total distance divided by total time. And that will give you average speed. It's not a great question, but when it comes to average speed, they will calculate the speed for the onward journey, calculate the speed for the return journey, and speed for the onward journey plus speed for the return journey divided by 2. This is what they will give as an answer. This clearly shows that they have not understood the concept. And this is what we need to do in the schools. Whether there is a policy or not, we need to do that. I think there's a great amount of work that we need to do. Maybe sometime under the auspice of Vijnana Bharati, we can talk about the teaching in the schools. Yeah.
Yeah, thank you, Professor Jagtap sir, for such an illustrious presentation about Acharya P.C. Ray. There is one thing about science, and then there is one thing about academicians, that they are best when they are brutally honest. And in Professor B.N. Jagtap, we had that kind of scholar with us today. There is one thing which I missed before thanking him. We were on NEP just now. I didn't mention in the introductions that Professor Jagtap has been instrumental in quite an important initiatives in higher education in state of Maharashtra. In fact, the perspective plans of the universities in the state have been prepared under his guidance, which I missed in the introduction, which
Oh,
must be
that's fine.
mentioned in the
That's fine.
context of NEP, because those are going to be an important integration sector. So I must mention that. And we have enjoyed the talk, sir, and we could see in the comments that even the entire audience has been glued to the presentation. All the right things about the chemistry, ancient chemistry, contribution of Acharya PC Ray came through. And he said one of the most important thing, sir. You said that this HCQ controversy was led to rest by none other than Professor Jagtap. That was the best thing to do, because we must talk about things which we have actually done, and done in an absolutely in a transparent manner, and that was put forth through this presentation. I thank you wholeheartedly on behalf of Vijnana Bharati, the entire audience which has been here today, and we would remain grateful to you forever. Thank you, and wish you all the best, sir.
Yeah. Thanks a lot. Thanks a lot.